Welcome back to the wonderful world of astronomy. This is chapter 4, Making Sense of the Universe. And in this chapter, you are getting your introduction to the concepts in physics that are necessary for understanding astronomy. And this video, we'll do chapter 4, part 2, Newton's Laws of Motion. Our goals for learning: how did Isaac Newton change our view of the universe? And what are Newton's 3 laws of motion? So let's talk about how Isaac Newton changed our view of the universe. Isaac Newton, who lived from 1642 to 1727, he was pondering, what is it that makes the moon move across the sky? And he was also pondering, what is it that makes an apple fall down? The legend has it he was sitting under the tree, as you can see in the animation, and he got hit in the head with an apple. Well, probably not, but he was pondering an apple falling. And he realized that this force that we call gravity, it's the same force that pulls an apple down. It's the same force that moves the moon across the sky. And that's an astounding leap that he made, because the moon and an apple are two very different things. Their motions are very different. An apple falls straight down, fast. The moon moves very slowly across the sky. Not only that, but the apple is seen as it's something on the earth. It's something in our world, whereas the moon is something up there in space. And it was always believed that whatever's up there in space, the planets, the stars, and the moon, they obey different laws. They're in a world all to their own. So an important contribution, what Newton did, was he realized that the same physical laws that operate on Earth also operate in the heavens. And this was the beginning of what's known as astrophysics, taking the laws of physics as we learn them on Earth and applying them to the things up in space. So he mentally bridged that gap between the things on Earth and the things up in the heavens. He discovered the laws of motion and gravity, and he did much more. He did experiments with light. He learned a lot and taught us a lot about the nature of light. He built the first reflecting telescope. Now, that doesn't mean the first telescope, but a reflecting telescope is a certain type of telescope that we'll talk about later on in the semester. He invented calculus, which was actually needed because as he was pondering and trying to theorize and come up with the mathematical equations that would describe gravity and describe the moon's motion across the sky, the math of the 17th century wasn't advanced enough to handle that. So he invented calculus to be able to describe gravity. So in pondering motion, he came up with what's known as Newton's 3 laws of motion, and they are recognized as valid today. So let's talk about them. The first one, Newton's first law of motion: an object moves at constant velocity unless a net force acts to change its speed or direction. And these are concepts already talked about in the last video. Let's break this down. Constant velocity. Now think about what that means. Remember from the last video, velocity is speed and direction. So an object that's in motion will keep the same speed. It will keep the same direction unless a net force, meaning a non-zero force, acts to change its speed or direction. So an example is a spaceship. If we launch a spaceship to the outer realms of the solar system, it doesn't need rocket power to go through the solar system. Once we set it on its course, we fire the rockets, get it up to speed, send it in the direction, it doesn't need rockets or fuel anymore. It'll just keep on going until, if some planet's gravity pulls it in, or maybe some asteroid hits it, that'll change its velocity, but it'll just keep going in the direction that it does. So think about in science fiction, oftentimes, like in Star Trek, they'll be flying along and they lose power, and then they come to a stop. But that's not how Newton's first law of motion works. If you're going at a great speed up in space, and you lose power, well, you didn't need power to keep you going. You would just keep on going. In fact, you would need power, you would need reverse thrusters to bring you to a stop. Newton's second law of motion. I think of this as a mathematical expression of the first law. The first law said that you need a force in order to change velocity. That means you need a force in order to give something acceleration. Newton's second law quantifies how much acceleration you get. Newton's second law in its simplest form is known as this: force equals mass times acceleration, F equals ma. And what that means is the net force applied to something equals its mass times its acceleration. But let me give this to you in a different way in terms of the cause and the effect. So the cause is on the right-hand side of the equation. The force that you apply to something divided by its mass, that gives the acceleration. So what that means is the more force you apply, the more it's going to accelerate. And you know that from everyday experience. If you want something, you want to speed something up, maybe you're pushing a cart, maybe you want your car to accelerate more, you give it more force. You push it more. In the case of a car, you press down on the gas pedal hard, but you know if you want it to go faster, if you want an acceleration, you apply more force. And that can also be negative acceleration. If you want to bring your car to a stop readily, you want a big negative acceleration, you apply a large force to the brakes. Now that is offset by the mass. Notice mass is in the denominator. So the larger the mass, the less acceleration you're going to have. So you apply a force to something of low mass and it will have a lot of acceleration. You apply the same force to a higher mass and it won't accelerate as much. Newton's third law of motion. For every force, there is always an equal and opposite reaction force. Sometimes it's stated this way: every action has an equal and opposite reaction. What I want you to understand here is that whenever there is a force, there's always a second force. They always come in pairs. And let's go back to what a force is. A force is the push or pull acting between two objects. And so if someone throws a punch through the air, and I've been asked, like with boxing, punching, how much force did that punch have? Well, if it was just flying through the air, it didn't have any force. It doesn't have any force until it hits something, till it pushes on something. It has energy, but not force. The force involves the push between two objects, or the pull. And so whenever object A pushes on object B pushes back on object A with an equal force and opposite direction. So let's say you push on the wall. You push on the wall, let's say to the direction north, you push on it with 10 pounds of force. The wall is pushing back on you, 10 pounds of force, but to the south. Now let's look at this picture here. It says a rocket is propelled upward by a force equal and opposite to the force with which gas is expelled out its back. The reason the rocket accelerates upwards, it doesn't push off of the launch pad. In fact, there's no launch pad anywhere near the picture. But what's happening is it is expelling hot gas out of the back. So we can say, in terms of stating Newton's third law, this example, we can say the rocket expels the gas downward. Newton's third law says the gas is pushing the rocket upward. And here's an example of somebody on a skateboard with the fire extinguisher. So a good example of rocketry right there. The fire extinguisher is expelling gas in one direction. The gas is pushing the person in the other direction. We also see this example with recoil from guns. You shoot a gun, Newton's third law says, if the gun shoots the bullet to the left, The bullet is shooting the gun to the right, so you can't just hold a gun loosely like this person is. You need to hold it tight because it will have that recoil based on Newton's third law. Thought question. How does the force the Earth exerts on you compare with the force you exert on it? We're talking about gravity here. Your weight is the force that Earth is pulling down on you. And later in this chapter, we'll talk about the nature of gravity. But the Earth pulls down on you. And let's say you are 150 pounds. The Earth is pulling down on you with a force of 150 pounds. So how does that relate to the force you exert on the Earth based on Newton's third law? Well, it's equal and opposite. So that means you exert a force of 150 pounds on the Earth, pulling it up. Now that sounds really weird to think you exert a force on the Earth, that you have this pull up on the Earth, because the Earth doesn't seem to notice your existence. You definitely notice the Earth's gravity, but does the Earth really notice your gravity? Well, the answer to that is that while you are pulling up on Earth, and let's just use the example of a 150-pound person, go back to Newton's second law. Acceleration is force divided by mass. The Earth has a mass of 6 trillion kilograms. A 150-pound person only has a mass of something like 70 kilograms. And so that 150 pounds of force has a lot of acceleration on the 70-kilogram person, but it has negligible, close to zero acceleration on the 6 trillion kilogram Earth. Another thought question. A compact car and a Mack truck, big semi-trailer, have a head-on collision. Are the following true or false? So question 1, the force of the car on the truck is equal and opposite to the force of the truck on the car. And that is a perfect expression of Newton's third law. So number 1 is true. What about number 2? The change of velocity of the car is the same as the change of velocity on the truck. Change of velocity, remember, is acceleration. Newton's second law says acceleration of an object is equal to the force applied divided by the mass of that object. So the car and the truck apply an equal force to each other, but the truck has a larger mass, so it's not going to accelerate as much. So false. In this video, what have we learned? How did Newton change our view of the universe? He discovered the laws of motion and gravitation. He realized these same laws of physics were identical in the universe and on Earth. And what are Newton's 3 laws of motion? And make sure that you remember these 3 laws of motion. They're very important for our study of astronomy. Number 1, an object moves at constant velocity if no net force is acting on it. Number 2, force equals mass times acceleration. And number 3, for every force, there's an equal and opposite reaction force. Let's talk now about conservation laws in astronomy. Our goals for learning: why do objects move at constant velocity if no force acts on them? What keeps a planet rotating and orbiting the sun? And where do objects get their energy? We talked a bit about this in the previous video, but let's get more into it. Why do objects move at constant velocity if no force acts on them? Objects continue at constant velocity because of conservation of momentum. So I talked about momentum in the previous video. And let's look at this billiard ball, these 2 billiard balls. And the first ball has some momentum. This is linear momentum. It's mass times velocity. And the second ball is just sitting there with 0 momentum. When they collide, the first ball is going to impart its momentum to the second ball. And so once they collide, the first ball has 0 momentum. The second ball has m times v. But you notice that total momentum was conserved. Regardless of which ball had the momentum, the total momentum in the top picture is mass times velocity. And in the bottom picture, after the collision, it's still mass times velocity. And so momentum was conserved. The total momentum of interacting objects cannot change unless an external force is acting on them. Well, what does that mean? First of all, if you just consider the yellow ball by itself, don't even think about the white ball. The yellow ball from the before and after picture, it does change momentum, but that's because an external force came in and from the white ball came in and hit it. But if you consider the system to be the white and the yellow ball, no external force, meaning some third party, came in and gave a push, and so momentum will be conserved. Interacting objects exchange momentum through equal and opposite forces. So this goes back to Newton's third law. The white ball exerted a force on the yellow ball, thus increasing its velocity. The yellow ball exerted a force on the white ball, thus decreasing its velocity, and in the end, momentum was conserved. What keeps a planet rotating and orbiting the sun? And again, we talked a bit about this in the previous video. Remember that angular momentum is mass times velocity times radius. So as the Earth orbits the sun, as I showed in the last video, if it's far away from the sun, and this is a definitely embellished picture right here, the Earth doesn't vary this much in its distance from the sun. It actually only varies by about 2%. It goes between 91 million at perihelion and 95 million miles at aphelion, so it doesn't change that much. But in this embellished picture, you can see a large radius, large distance from the sun means it's going to be a smaller velocity. And a smaller distance means a greater velocity. But between the two states on the left and on the right, if you take the mass of the planet times its velocity times its radius, whether here on the left or here on the right, it will be the same amount. The angular momentum of an object cannot change unless an external twisting force, which is known as torque, is acting on it. And so if you think about what would it take for the Earth to change in that orbit, well, it would take something massive, maybe the gravity from a passing black hole. We don't expect that to happen, but a strong gravity, or maybe some cataclysmic collision of something very big against the Earth. That would be an external torque. But aside from those things happening, the Earth is just going to keep on going around the sun the way it does. Earth experiences no torque as it orbits the sun, so its rotation in orbit will continue indefinitely. Here we have something that Albert Einstein theorized this in 1915, and it was first demonstrated experimentally in 2015, so it took 100 years for his theory to be experimentally shown. But this is a simulation of two black holes or neutron stars, very highly, with strong gravity, very dense objects in space, and they're in orbit around each other. And as they come in closer and closer, they speed up. And that's a good example of conservation of angular momentum, that together, the system between the two of them, there is angular momentum, but as they come closer and closer, going towards collision, think of it as the radius decreases, so the speed increases. That is the end of part 2, Newton's laws of motion. Have a great day.